thanks for tuning in to BEaTS Research Radio, a podcast and YouTube channel that aims to disseminate science and research to the community. My name is Nicole Chu, your host for today's episode. Today, we are honored to be joined by Professor Andrew Cooper. Professor Cooper was elected as a Fellow of the Royal Society in 2015 and is currently a Professor of Chemistry at the University of Liverpool. He is the founding director of the Center for Materials Discovery and the academic director of the New Materials Innovation Factory. He is also currently the principal investigator of the Cooper Group at the University of Liverpool, and his pioneering research work in materials chemistry focuses on polymer synthesis, nanoparticles, and crystal engineering. In 2011, he was named one of the top 100 material scientists of the last decade in the Thomson Reuters list. In 2021, he was awarded the Super AI Leadership Award, which was previously won by IBM Research for his robotics work on the mobile chemist that was published in the journal Nature. Thank you so much, Professor Cooper, for joining us today.
Thank you.
It's an honor to have you on our channel. So to start us off, for those who may not know, can you please explain the main focuses of the Cooper Group's research at the University of Liverpool?
Yeah, well, we do a few different things. We are interested in materials, new materials for applications such as energy and sustainability. But I guess the topic you mentioned in your introduction is mobile robot scientists. And there we've been building intelligent robots that can carry out experiments by themselves and can ultimately search for useful materials.
Oh, okay. So you and your team, as you mentioned, developed this mobile robotic chemist that is able to conduct experiments without any minimal human intervention. Do you mind sharing how this idea came about?
Sure. Well, it really came from our materials chemistry research. So we were looking at the time, and still looking for catalysts that can make hydrogen from water using sunlight. So the idea is to create clean energy. But the practical problems of doing this are very large. There are an enormous number of practical concerns about scaling up these catalysts, making them work in a way that could be used in a real system. And essentially the problem's just too big. There are too many variables, there are too many possibilities, and the design space is too big. So we came to the conclusion that we needed a method that could look much more broadly, many more candidate materials. So that's when we decided we should build a robot chemist.
So you have this idea, and how does the robot function? How is it being used to assist in material chemistry research?
Well, in the first example that we published in 2020, the robot works entirely by itself. You give the robot some starting materials, some chemicals, and then it is programmed to find better catalysts, and it goes around and around in a loop without any input from the human. So it works entirely by itself. And it looks at a very large space very efficiently using an algorithm to search the space, and ultimately found new catalysts which perform better. But in the future, we want to move away from that actually and have a system where the robot works with researchers rather than instead of researchers, because robots are very good at some tasks. They're very good at performing automated tasks over long periods, and they can also think in high dimensional space where you have very large numbers of dimensions. But they're not very good, or artificial intelligence is not currently very good at seeing even simple links between concepts, drawing conclusions, making new hypotheses. So what we want to do in the future is blend these two approaches together. So to have, rather than a robot working by itself, have a robot working in collaboration with researchers, with human researchers.
Oh, so the last part you mentioned, having this robot working in collaboration with researchers, your team started out automating this mobile chemist, focusing on the itself rather than technological instruments. Why was that?
Yeah, well, there were a couple of reasons there. One simple practical reason is that in materials chemistry, but also in biology and other applications, the range of instruments that are used is very broad, and they're really all designed to be used by humans. So the lab instrumentation market value is something like $16 billion a year. And basically 99.99% of that is built to be used by humans. So while you can convert lab instruments to automated systems by modifying them, it gets complicated, it gets expensive, and we wanted something that we could drop into an existing lab and use the equipment that we are using now, largely. And there are lots of advantages to that in terms of flexibility, cost, speed to deploy it. Every time you build a new machine, it takes a long time and money. So we really wanted to be able to move fast and set up workflows quickly without building some huge monstrous machine, which occupies the whole lab. So our conclusion, which seemed crazy at the time, but less so now, is automate the chemist, not the instruments.
Oh, I see. So looking at some of the videos online of your mobile robotic chemist, it seems to have like one arm that is able to move around with minimal human intervention. How many designs did your team undergo to ultimately end up with this finished product?
Yeah, well, the robot we didn't build ourselves. It's a commercial robot, but to make it work in a lab was a long and slightly torturous process. So the main challenge really is not so much that it only has one arm. It's you need to have very high precision. So the robot has to put, little reaction vials into holes in a reaction block, and essentially you need sub-millimeter precision, so much less than 1 millimeter. And in the experiment we published, the robot travels something like 2.5 kilometers over the 8 days that it's working. So it's moving around a large lab, accessing multiple instruments. And basically it has to be exactly in the right place every time. And that's quite difficult. It's analogous to these robots I'm sure you've seen in warehouses, which put a box in one place, but there, the precision could be a few centimeters, whereas here we had to make it very precise without going through all the pain and details. It took a lot of engineering and feedback loops to make that work.
Oh, I see. So is this robot designed to be working alongside researchers at the same time in the laboratory?
Yeah, well, it wasn't really designed to be used in a laboratory, and until we did this, these robots weren't used in labs, but it is designed to work with humans. It's something that people call a cobot or collaborative robot. So it has a variety of sensors. So if you tap it on the side of the arm, it stops. It's designed to be used in proximity of humans safely. We also program it to move slowly because it weighs 400 kilos. So, it needs to be relatively slow in the lab because it's got a lot of momentum otherwise. But yes, it is certified to be a collaborative robot or cobot.
Wow, 400 kilos, that is a lot.
Yeah.
So
yeah, you need a stable floor as well in your lab, otherwise you have a problem.
Can't put it too high up or else the floor might give.
Yeah, I wouldn't necessarily put it in an elevator. That's right. Yeah.
So we've been speaking about specifically your mobile robotic chemistry. However, moving forward, is there a specific direction that you hope to see the automation of chemistry research move towards?
Yeah, I mean, we've got two main thrusts, I guess. There are some limitations to what we published 2 years ago. For one thing, the robot or the AI really doesn't understand the chemistry. It's optimizing a mixture. It could almost be making a cake or a cocktail. It doesn't actually understand what it's mixing. And that's a big limitation. So we're looking to build in physical models where the artificial intelligence doesn't just optimize things, it predicts that this material will be better than this material. So effectively, it knows what it's looking for and to some extent why. The other thing I guess I mentioned already is to have collaborative systems. We sometimes call it human in the loop. So imagine an optimization where the robot is doing a long-term search over some months or even multiple months. And a team of humans can interface with the software and say, yeah, okay, we can see some trends here that maybe isn't apparent to the artificial intelligence and inject their knowledge into the experiment, which will be much more powerful, we believe, than a robot working by itself, because it's just incredibly difficult, I would argue impossible, to capture even a fraction of the chemistry knowledge that researchers have currently. So we want to inject that into the experiments as they happen. And that's the thing I think I'm most excited about for the future.
Absolutely. Thank you so much for sharing more about your research on this collaborative robot initiative.
Thank you.
Thank you, Professor Cooper, for joining us. And thank you to all BEaTS Research Radio listeners for tuning in. Don't forget to like and subscribe to our YouTube, Twitter, and Instagram channels at BEaTS Research. On behalf of our entire radio team and director, Dr. Emilio Alarcon, we hope to see you all next week. Thank you.